Hello, and thank you for watching. My name is Oliver Philcox, and today I'm going to be discussing two recent papers I've been involved with, both concerned about a measurement of H0 from galaxy surveys, both with and without the sound horizon at recombination. To give you a little bit of background about myself, I'm a PhD candidate in Princeton, having previously spent some time in the CFA in Harvard, as well as Cambridge University. I'm primarily interested in large-scale structure theory, but also dabble in analyses, such as the results of these works. So to begin, I should briefly thank my collaborators, in particular those of the top row for the paper without the sound horizon, and those of the bottom row for the paper with the sound horizon. The H0 tension needs no introduction in modern-day cosmology. For now, all I would like to say is that the measurements can generically be split into two types. I'm going to refer to these as indirect and direct measurements, with indirect measurements being possible through some cosmological model, such as lambda CDM, and direct measurements being model independent, for example, those from the cosmic distance ladder, strong lensing, or gravitational waves. Now, for indirect measurements, for some decades, the canonical observations used for these is the CMB. And in the plot on the right here, I'm showing two recent CMB experiments, Planck and ACT plus WMAP, and the H0 constraints. You see they're peaking somewhere around 67 to 68 with relatively well-constrained error bars. For reference, on the right, I'm showing the latest results from the SHOES collaboration from the distance ladders. And you can see immediately that these are in some tension. Now, whilst CMB has historically been the most important player in the indirect field of measurements, this is no longer the case. Today, we have a whole host of measurements from large-scale structure, which are now comparable in constraining power to those from the CMB. So I've just plotted a few of these here. For example, taking the BAO scale from BOSS, taking the full shape from BOSS, or some more novel experiments. And I'm going to be discussing these in more detail later. To fully understand how we can get information from galaxy surveys, we should start off by thinking about the matter power spectrum. So here, I'm plotting the matter power spectrum at redshift 0. And if you glance at this, two scales should immediately come to mind. Number one, the equality scale. This is clearly the peak of the power spectrum, and it corresponds to the horizon size of the universe at the epoch of radiation matter equality, so when the radiation density is equal to the matter density. This both sets the peak of the power spectrum and the overall broadband shape. The second scale is the well-known sound horizon. This is a feature sourced around a redshift of 1100, and crucially, it sets the frequency of Baryon Acoustic Oscillations, these wiggle features you see in the spectrum. Now, in general, both of these features could be used as standard rulers to constrain cosmology, because we can predict them from theory and we can measure them from data. That sort of standard ruler will allow us to place a constraint on H0. In the last 2 decades, cosmological analyses have focused on the sound horizon, especially probes such as BOSS and eBOSS, making extensive and exquisite measurements of the sound horizon parameters. So let's think a little bit about how they do that. This is where I start the first part of this talk, which is H0 from the sound horizon. So before going into too much detail about how the measurements are made, it's worth considering the dataset. So throughout this talk, I'm going to be focusing on one key dataset, which is the power spectra from the 12th data release of BOSS, as plotted here. So they come in 2 regions of the sky, in the north and the south, across 2 redshifts, and span a volume close to 6 cubic gigaparsecs per h cubed. What you can see here is the power spectra both before and after reconstruction. The reconstructed power spectra, you can see, are slightly more wiggly, and I'll come into a greater discussion of these later. It's worth saying at this point, this data is only the beginning. In the next decade, we're going to get a massive amount more data with surveys such as DESI and Euclid. this total volume will increase by a factor of at least 10. So now, to give you information about BO analysis, what happens? So the recent surveys such as BOSS and eBOSS generally constrain 3 parameters. There are 2 scaling parameters, known as the Alcock-Paczynski parameters, here alpha parallel, alpha perpendicular, as an additional parameter f sigma 8. Now these scaling parameters can be thought of as scaling of some fiducial power spectrum both along the line of sight and tangential to the line of sight. For example, in this plot on the right, I'm showing the ratio of power spectra to their smooth spectra. And the effect of this alpha parameter is to contract or dilate these wiggles along the k-axis. So by comparing our physical model to the data, we can measure the scaling parameter, which itself is going to tell us something about cosmology. So you see here, these parameters depend on the Hubble parameter, h of z, and the angular diameter distance, d of a. However, in order to extract a measurement of h0, we need to know this sound horizon appearing, rd. Generally, the analyses either fix this from Planck or use some priors, for example, the omega b prior from Big Bang nucleosynthesis that effectively sets the sound horizon rd. Now these is spectra before reconstruction. When we add reconstruction, what happens is that the spectra get sharper and sharper wiggles, seen by this flicking between the 2 slides. See that the axis of density field reconstruction sharpens the wiggles. This is exactly what it's supposed to do. To give you a 1-sentence introduction to reconstruction, the idea is that we take the galaxies and we displace them back to closer to their positions earlier in redshift. So for example, between redshift 10 and redshift 1, galaxies will have moved from large-scale bulk flows. We try and undo this bulk flow, which is going to effectively sharpen the BEO wiggles. This naturally is going to give us better constraints on our scaling parameters. Now, the question that's been asked extensively in the last couple of years is there more to a galaxy survey power spectrum than just the BAO? In particular, can we constrain information from the full shape of the spectra? For example, this full broadband shape, including the wiggles I'm showing on the right. In order to do this, we need a model for the power spectrum. Something the Zaldariaga group has been interested in is how we can do this, involving the effective field theory of large-scale structure, which has been rigorously developed over the past decade, with components including one-loop perturbation theory, a non-linear bias model, stochasticity contributions such as shot noise, UV counterterms to parameterize the effects of small-scale physics on large-scale modes, and infrared resummation to account for large-scale bulk motions of galaxies. Schematically, the model looks something like this: a combination of linear theory, one-loop effects, shot noise, and counterterms. And for full details, I'd encourage anyone to go and look at these papers, which deal with the application of this to BOSS galaxies. It's worth saying that this model has been tested extensively on huge volume simulations, such as in the recent paper Nishimichi et al. And we see excellent agreement between the simulations and data in a volume larger than the observable universe. So what do we do with this? We take a galaxy survey, and we take the EFT model, and we combine them using MCMC, including some prior on the omega baryon parameter. We can get constraints on cosmology. This is the plot taken from the Ivanov et al. 2019 paper, and you can see that focusing on the H0 constraints, the constraints possible from BOSS are relatively similar to those from the Planck analysis. Indeed, later papers have shown that combining Planck and BOSS will give you even better constraints. This is good. We're using the full shape of the power spectra to extract constraints on cosmology. However, what about this reconstructed spectrum? I previously said that this was good for squeezing out even more information by sharpening out the BAO wiggles. Could we do this in our full shape model? Turns out this is difficult. When we do the reconstruction, it tends to distort the broadband shape. Secondly, this distortion depends on the reconstruction scheme we've applied. and also on modeling assumptions. So this isn't particularly useful, although there's been significant work devoted to modeling this, for instance with these papers here. So we were interested in how we can add in the reconstructed power spectrum information without having a full model for it, because as yet, no effective field theory model exists for the reconstructed spectrum. We have a solution. The solution is in two parts. The first is to take reconstructed power spectra and measure the BAO scaling parameters, so these alpha parameters I mentioned before, and then take those parameters and simply feed them in to the full shape likelihood I previously discussed. So now, instead of just analyzing a power spectra, we analyze a power spectra plus two BAO scaling parameters with some joint covariance matrix, which you can get from data or from simple modeling. Combining these two together is going to give you constraints on cosmology, crucially allowing more information to be extracted from BOSS. So to show this in practice, let me show you the posterior plots. This is in the omega-CDM H0 plane, where the full shape likelihood is particularly sensitive. What you notice is going between this gray and this blue contour, we notice a significant dilation, especially in H0. Indeed, adding the BAO information to the full shape likelihood allows us to extract more information with tightening of the error bar by 40%. This is equivalent to doubling the survey volume. It shows that techniques like this are very powerful if we want to extract the strongest constraints possible in cosmology. Now, let me move to the second part of the talk at this point. I've talked extensively about how we can measure H0 using the sound horizon and the BAO. But what about making a measurement without the sound horizon? I'd like to return to this earlier figure, and I said that there were two scales encoded in the matter power spectrum. Let's think about the second equality scale. Can we use this to do cosmological inference? So the equality scale contains H0 information. If you look at its fundamental form here, you see it scales as the density of CDM plus baryons times by H0 squared times by the temperature of the CMB, which we assume to be well known. So a measurement in H over megaparsec units necessarily probes this combination. Thus, if we have a probe of omega CB, or more commonly omega matter, we can constrain H0. Interestingly, this is a measurement of H0 anchored around the equality scale, around redshift 3600, much earlier than that of BAO analyses, which measure at redshift 1100. This is crucial. New physics acting around redshift 1000 should affect BAO and equality measurements of H0 differently. This may give us an indication whether new physics models of the Hubble tension can actually solve the problem. To give you an example, it's a plot from one of the recent early dark energy papers. I'm showing the fraction of early dark energy in the universe as a function of redshift. You see between these two lines here, between the equality scale and sound horizon scale redshifts, there's a huge change in the amount of dark energy. And it's quite likely that this change would lead to a different H0 being measured at these two anchors, thus providing a powerful test of cosmology. So how do we measure this equality scale? I should first off say it's actually been measured decades ago. The early power spectrum analyses of the turn of the 21st century measured the shape parameter gamma, which encodes the equality scale. A recent paper by Baxter and Blake Sherwin showed extensively that this could be measured from Planck lensing. There, they measure the projected equality scale, L equal, which has a slightly different scaling. But we're able to use that to get H0 constraints independent of sound horizon physics. And a lot of the paper was devoted to discussing why and how they could show that this indeed was independent. These are the constraints on the right. See that combining Planck lensing with the Pantheon supernova sample to give you omega matter information gives you some constraints on H0. Now, the question then is, can we do this for the current generation of galaxy surveys? And importantly, can we do this to get H0 information from the equality scale whilst remaining independent of sound horizon physics? Now, naively, you would think that this would give you much stronger constraints than from lensing because we have more modes available. So let's see. The difficulty is that we can't see the equality scale directly in BOSS. We can't resolve low enough K modes, they're subject to systematics and other effects, so they're generally removed from the analysis. However, the equality scale is probed from the power spectrum shape. So this is a really rough estimate of the large-scale shape of the power spectra on scales smaller than equality. And you notice that it's not a pure power law. It has some non-trivial dependence depending on the log of K over K equality. Given some knowledge of the amplitude, which comes both from loops, redshift-based distortions, and some weakly restrictive priors on AS, we can measure the equality scale. Furthermore, adding information about omega matter will break the degeneracy between H0 and omega CB, and thus give us an H0 constraint. We have one ansatz with this. We're going to assume that analyzing the full shape BOSS data without a restrictive prior on the baryon density will measure H0 from the equality scale. Let's see the resulting constraints. So at this point, I'm going to show you the constraints on H0. And first, I'd like to stress that we're not just constraining H0 in this likelihood. We're varying, in fact, 34 parameters, including 28 nuisance parameters, as well as also the baryon density, the CDM density, the primordial power spectrum amplitude and slope, as well as the neutrino mass. For full details, I'll direct you to the paper. So these are the key results of this work. In red and blue, we see the constraints from BOSS, coupled with omega matter priors, firstly from the Pantheon supernova sample, and secondly from uncalibrated BAO. It turns out it's possible to use the BAO in a manner where we don't tell it any information about the sound horizon, which then only gives us information about omega matter. In green, I have a combination with Planck lensing, which is shown by itself in the peach contour here, from the original, very similar to the original constraints from Eric Baxter and Blake Sherwin. So these are the 1 sigma results. I will note that these posteriors are clearly very non-Gaussian. So as ever, for non-Gaussian posteriors, 1 sigma results should be taken with a grain of salt. However, it is interesting that we are obtaining H0 constraints from galaxy surveys and omega matter priors alone of the order of 65, 65.5 plus 3 minus 5. Now this is particularly interesting because 95% of this baseline posterior in red is below the shoe's best fit, despite the fact we have assumed nothing about the sound horizon. And as I'm going to show you in a minute, the sound horizon does not change our constraints. So that's an exciting result. So let me talk more about this sound horizon independence. We should try and test how we can work out if we really are independent. And one good way to do this is to use mock data. So we're going to consider 3 sets of synthetic data. The first, set up to match BOSS DR12 approximately. The second, with suppressed BAO wiggles. And the third, with 10 times less baryons. Options 2 and 3 are considered because they effectively remove the sound horizon information arising both in BAO wiggles and the baryonic power spectrum suppression. When we look at the H0 constraints from these, we see the constraints are incredibly similar between the 3. Seemingly removing baryonic damping or removing BAO wiggles has virtually no effect on our H0 constraints. And this indicates that information is not coming from the sound horizon. However, we weren't content with these constraints alone. So for a second test, we looked at Fisher forecasts. Now we're doing a simple analysis for BOSS, but instead of using the linear power spectrum, we're going to use the transfer function from Eisenstein and Hu. Consider 2 datasets, the first emulating BOSS DR12, but the second explicitly marginalizing over the sound horizon. And this is the reason why we use this transfer function, because the sound horizon appears explicitly allowing this marginalization. Constraints are shown in the right here. we notice almost no difference between the red and the blue posteriors, again telling us that when we marginalize over the sound horizon, nothing happens. Information is not coming from the sound horizon. Indeed, in the paper, we then mention a third test, which is to do with scale cuts. The results are very similar, and I'll direct you to the paper to see more. At this point, it's worth thinking about the cosmological implications. So as previously mentioned, BAO constraints are a probe of H0 anchored at redshift 1100, whilst equality constraints are a probe of H0 anchored at higher redshift, around 3600. A discrepancy of H0 constraints between these two redshift anchors could indicate new physics happening around recombination. Conversely, consistency of H0 measurements would make beyond lambda CDM solutions to the Hubble tension more difficult. Right now we see consistency, and it will be particularly interesting to see if this extends to higher precision. Of course, we're going to get more data soon. Simple forecast for Euclid shows that constraints of the order of 1.5 kilometer per second will soon be possible. And indeed, measurements like this may be able to place strong bounds on solutions to the Hubble tension. I'd like now to summarize and finish up by saying that galaxy surveys can place strong constraints on H0. It's no longer just the CMB, and it's no longer just the BAO. As I showed in the first part of the talk, combination of BAO and full shape data with BBN priors on Baryon gives H0 constraints of the order of plus or minus 1.1, sitting around 68. These take a lot of information from the sound horizon scale, but we can also do it without the sound horizon scale by combining the galaxy surveys with Pantheon supernova sample or uncalibrated BAO. This gives us H0 around 65 mark, independent of sound horizon physics. So I'd like to say thank you very much for watching, and I'd be very happy to answer any questions by email or any other method.